Okay, so thank you for the nice introduction. So yeah, today I'll be talking about what Ken said, but before that, this is a very boring slide because I wanted to do an experiment. If you can, I would like you to scan this QR code and think about the 3 first words that pop into your mind when you hear astronomy. Please use single words so that everyone has the same words coming up. No, too much thinking, right? The first words.
Just one word.
3 words. No, you can use like a flower pot, for example. I wouldn't relate that to astronomy, but yeah. Okay. Does everyone have their words ready? You can you like change the yeah, that one, and then show response. Ooh, the tension. Here we go. So this is what you all answered. So I see a lot of people think about space, stars, the universe. So this is actually already quite a diverse set word cloud, because I do this experiment quite a lot, and usually the word cloud contains like only 5 or 6 words. So now I want you to kind of keep in mind your biggest words together, and I'm going to move back to my presentation, where I have asked 120 astronomers the same question. Yeah. And this is what came up. So a lot more words, right? But the first thing that I at least see is that stars is also one of the biggest ones. Space, I know it's in there somewhere. Universe as well, like right there. So we have, I think the big lines are more or less similar, but of course it's our job. We do this daily. We're all fixed in a tunnel vision. Well, not really a tunnel vision, but you know, we have our set words. And so today, the words that I'm going to be using during this presentation will be, well, stars, black holes, spectroscopy, which is a difficult one, but we'll get to it, and then binaries, as Ken already said. So fantastic black holes and how to find them. I don't know if you know this cartoon from the movie, but today we're going to kind of make me find some of the black holes. So as mentioned, a little background. So I did my studies and PhD at KU Leuven in Belgium. And maybe when you think about Belgium, a lot of people will think about chocolate, fries, waffles, and I guess beer, which is very famous. And maybe some people, they want to try and find some black holes by drinking a little bit too much beer, and they'll see some stars and black holes. Today, I'm going to do it in a little bit more of a scientific way and not in this way. So let's start with what kind of black holes, or what are black holes, basically. So do most people recognize this picture? What is it? The first image of a supermassive black hole was a very, very big discovery a couple of years ago. And this black hole is what we call, indeed, a supermassive black hole. So it's quite heavy, 10 to the 40 kilograms. I'm not going to give you a scale for that, just super massive. And we find them at the center of galaxies, also at the center of our galaxy. Now, how did we otherwise confirm this as well? And I hope this is going to work. So in the oh, does this work? No. Can you like click in the middle? No.
Play?
Yeah, play. Is it not working? No. Yeah, okay. So this is from the 1990s, right? And so we can see, I'm gonna drop this mic a bit. We can see quite a lot of movement here. I think already it's gonna play twice. And we're gonna zoom in. And the scale that we're looking at is what it says 10 light days, might not say a lot, but this is basically 500 million times going from Tokyo to Kyoto. And it's so far on the sky that what we are looking at is actually as if we would be seeing a 100 yen coin at Tokyo Disneyland, but seen from the skytree. So very, very precise, or well, for us, very small motion that we were able to detect. And so this is what it looks like. Can you like press the play button again? Yeah. So we can see here, for example, this star very clearly moving with these 10 light days. So basically, I don't know if you want to like play it again. So, oops. Well, okay, that's fine. You saw the motion. You saw the motion. It's fine. So we can really detect this. Now, there is a second set of black holes, which are what we call stellar black holes, and these are dead stars. Yeah, so they are much less massive, only 10 to the 31 kilograms. I'll come back to another scale later. So the ones that I'm going to focus on is the stellar mass black holes, so these dead stars. What is, if I ask you to stars, what is the first star that would come into your mind? The sun, exactly. The sun is what we call a low mass star. Why is that? So by definition, the sun is born with 1 times the mass of the sun. So it has 1 solar mass. This is a unit that we use a lot because it's quite heavy, 10 to the 30 kilograms. I don't really like thinking in these big numbers. So we just say solar mass. By definition, the sun is also as bright as 1 times the sun. So it has 1 solar luminosity. Very simple. Now, there are stars that are way more massive than the sun. This is what we call a massive star. They are born with at least 8 times the mass of the sun, and they will be 1,000 times brighter than the sun. So they are really the hottest, biggest, brightest stars in the universe. And let's put it into scale. Yeah? If this is the Earth, this very tiny dot, like even if you can't see it, it's a teeny tiny dot, then this would be the sun. Now, if this would be the sun, then this is a massive star. Yeah, so we're talking really massive, big scales. Now, these massive stars, they will end their lives. And how will they do this? They will go supernova. And for a lot of these massive stars, they will leave behind what we call a neutron star. So what is a neutron star? It's a very, very dense object. And I'm going to take the map of Tokyo. So I've highlighted, for example, Ueno, Shinjuku, Shibuya. Yeah, that's all on this map. And now I'm going to place the neutron star at the center at the Imperial Palace, kind of. So it would take about this area. So Ueno would be fully covered in it. It kind of reaches Shinjuku as well. But it's more massive than the sun. So it's a very, very compact, dense object. But that's only a neutron star. If we go more massive in our stars, for example, larger than 15 or 25 times the mass of the sun, yeah, we're going up, then we're going to end with a black hole, which is a very tiny object that has about 5 to 100 times the mass of the sun, at least these stellar mass ones, and they are about the size of the Yamanote line kind of area. So they are even denser and even more massive. And in this process, there is something happening, namely the production of elements, or what we call chemical enrichment. Now, what is chemical enrichment? So I guess we all recognize the periodic table of elements. Now, in the beginning of the Big Bang, there was only basically hydrogen and helium, maybe a little bit of lithium. So how did we get to all these things like gold, oxygen, just based on from these 3 things? Well, from this, we have this map, which we call the astronomical table of elements. And so it has a lot of colors, and they are coded by which stars or in which processes these elements are formed. And the ones that we can focus on are the orange and green ones. So we can see a lot of orange and a lot of green here, especially oxygen, for example, our dear oxygen, so important. Massive stars. So thank you, massive stars. And this is, I think, where the famous quote comes from, which we are all stardust, which is effectively completely true, because every element that we see, apart from hydrogen and helium, is basically thanks to our lovely stars. So how do we then search for these black holes now that we know what they are? And we're going to focus first on the Milky Way. So in Fantastic Beasts, you have this kind of nice map of all the elements. So we're going to map our fantastic black holes on this chart as well. I talked about the supermassive ones. I'm going to put them in here because they are, part of it, but I'm not going to focus on these, right? They're separate in their box. So let's take a little mock galaxy. Yeah, so these are all the stars. Now, black holes, they don't emit any light. So it becomes kind of difficult for me to say where the black hole is. Now, so what we have to do is try to find ways of seeing them. So unfortunately, our stellar mass black holes, they are much smaller, even though they are much closer. So we can't take a picture of them like we did with the supermassive black holes. We also can't trace the motion of the other star around them because they're just too small and there are not stars close enough. So we're going to have to think in other ways. So this here, if you can see it properly, is just the kind of wavelengths that we have in the universe. So we have very long wavelengths, the radio, and we have here very short gamma rays. And what this diagram actually shows is the longer the wavelength, the lower the energy or the temperature, which means that everything that is here radio is quite cold matter, and the more we go to the right side of this diagram, the hotter we get in matter. We humans, we radiate as well. We're kind of very cold here in universal scales, so we are more or less in the infrared. Stars, there are a lot of stars who are shining in the visible. We can see it when we look at the night sky, right? And I'm going to tell you that black holes, they may be at the X-rays. So why would they emit in X-rays? Because they don't emit any light, right? So sometimes what happens is that there is a lot of matter around the black hole, and this will heat up when it's accreting onto the black hole to like millions of degrees. So we're going to produce this very hot matter that will show as X-rays. The only question is how this matter would get here, yeah? And this is why we need another star. So if another star would be close enough, it can be dumping mass onto the black hole, which will then heat up and create our X-rays. So let's take a look at the galaxy. So this is just the visible light. This is how we would perceive it with our eyes if we would be able to see the full galaxy. You can see here, this is the Milky Way, this kind of. So you see more light coming from it here, a lot of dust where the black patches are. In the X-rays, if we would do exactly the same, the Milky Way is gone. We don't see the dust, we don't see all the stars, except for a few spots. Like, here there are a lot of these spots. The X-ray sources, they really stand out because the rest of the universe is fairly quiet in the X-rays. So we can very easily detect all these X-ray sources and hence find our black holes. So the first class of black holes that I'm going to put in this diagram is the X-ray black holes, the interacting ones. Okay, let's move on to the next one. So here comes spectroscopy, which I'm going to explain. So we're going to look at the spectrum of stars. Maybe you'll remember the experiment you did probably in high school where you put some light through a prism or something and you got out the very nice rainbow. We can do the same for stars. And if we have that for stars, like the sun, for example, you can see these dark lines in the spectrum. Yeah? These are very typical for the star. They indicate what kind of star we are looking at. But for us, it means something more. Because what we can do is we can look at how they move. So probably you notice that when the ambulance comes towards you and goes away from you, the frequency changes. Yeah? This is the Doppler shift. And sound does this, but light does the same. So when a star would be moving away from us, the wavelengths get much longer, much redder. And if the star moves towards us, the wavelengths get much shorter and much bluer. So these dark lines, when our stars move, we can they're constantly moving away and towards us, and we can see these black lines actually move in the spectrum. So we can have evidence that two stars are orbiting around each other. And if we're trying to look for a black hole, well, then we only need one star, right? We would only see one line move. So this is a sketch, but what would it look like in real life? So this is the same image, these black lines, except we don't fully see them black. We just see them as lower light, less flux. So this is two stars. You can see these two lines, and they flip as the star moves around each other. So this is a binary, two living stars, two shining sources. And if we would have a black hole, that would just be one thing moving, kind of. So this is how we would detect a black hole with spectroscopy. So this is my second category of black holes, the spectroscopic black holes. Now there is more. We can look at how the stars move on the sky. I know I said we couldn't detect the individual star really orbiting the black hole, but we can at least try to do something very similar. Oh, I already went to the next slide. Oh, that's okay. Yeah, so what you can see here, for example, is an image, and I know the lines are a bit faint, but I'll come to it. I'll have a better one later as well. But you can see the Big Dipper. We call it the Big Bear in Dutch. I don't know if that tells you more. But it's one of the constellations, and if we would look at it over a time span of like 100,000 of years, this is how it would move on the sky. Yeah, so we're going to do something similar, just on a much smaller scale, a couple of years, maybe 5 years. So the first thing that stars apparently do on the sky is what we call the parallax motion. It's just because the Earth rotates around the sun, so we're going to create this motion. And it's very similar to when you would be driving on the road in this very mountainous landscape. You have trees in the front. The trees will move much faster than the mountains in the back, which seem to just be standing there. And so the same happens for the stars. So if we look at the parallax, for example, if we go 6 months difference, a star that is much closer, here the red dot, will appear much more shifted than the other stars. And so this is what we call the parallax motion, and it's basically stars will just be moving in an apparent elliptical motion according to what we observe from Earth. The second thing is the stars are all moving in the Milky Way, but they might be at different positions in the Milky Way, which means they are moving at a different velocity from us. And so this is the sketch. So this is exactly the effect that we were seeing with like the Big Dipper. So if we look at it now, right, we all recognize this one. However, if we look 70,000 years ago, for example, these stars have not all moved in the same direction. And that is because we see it as a constellation, but they are effectively just at different distances from us in the Milky Way. So they'll move at a different speed. And on shorter timescales, if you look at the stars like this is what you get. This is what a single star would just be doing for us on the sky. It would just be spiraling around. Now there are binaries. And if we have 2 stars, things can get a little bit wobbly. Yeah? And so we're going to add this additional wobbling motion to this very nice spiral motion. And what we're going to get is something like this. Oh, sorry, do you want me to go back?
Oh, it's okay.
So a very deviation from this very nice spiral. Yeah? And I'm going to just tell you that for black holes, this spiral motion, this wobble, will be much larger than for 2 stars. And so this is how we're going to try to find black holes with astrometry in this specific method. And this is my 3rd class of black holes. Okay, so let's use our methods and try to find our black holes. So I'm going to go back to my mock galaxy here, where I have no clue where my black holes are. So the first thing we can do is look at the X-rays. Yeah? So we can take, for example, one of the JAXA space telescopes here and take a look at the X-rays. This is what it looks like. Everything basically goes dark except for this very one bright dot, which is effectively where we found a black hole. So this is the first black hole that was ever discovered. It was Cygnus X1. It was discovered already in the 1970s, yeah, and it really just looked like this. I mean, this is the X-ray image that we have. And so this basically tells us that this binary has, this black hole has another star next to it, which is dumping the mass on it, yeah? So it has a matter around it that's hot enough. So it was confirmed through spectroscopy, so we didn't do it only with X-rays, but what we then found is that it has a black hole of about 15 to 20 solar mass. We're not fully out of it, we can't fully say which one it is, but somewhere along these lines. And then a star next to it, which is roughly 30 solar mass, maybe 20 solar mass, depending on which year and who you ask. But the orbit is very short. It's about 5 days only. And this is very typical for the X-ray binaries. X-ray binaries, they need this other star nearby. So naturally, we want them to be short to each other, so very, very short orbits. orbit, few days. Let's look at the next method, astrometry. For this, I want to highlight a telescope, which is the Gaia telescope. It has basically observed the motion of 2 billion stars in the sky, yeah? And it can do so with a precision as if it could detect a coin on the moon. Yeah? So if you move the coin on the moon, Gaia could detect the difference in motion. So it's a very, very important instrument for us now in these years, very, very high quality data. So this is what Gaia would tell us, kind of. So we had this black hole here, right? This X-ray black hole. With Gaia, we don't see this. But we do see another one. We have another one right here. And this was the closest black hole to Earth so far still. We named it a very beautiful Gaia Black Hole 1 because it was the first black hole discovered by Gaia. We are very original in our names. And I say it's only 1,500 light years away. So this is light years is the distance light can travel in 1 year, which is a lot. It might not give you any idea of what this is, but I'll give you two references, which is that the closest star is about 4 light years, and the center of the galaxy is about 26,000 light years away from us. So in astronomical terms, this is relatively close. Yeah, this is basically in our backyard at our neighbors or something. So very nice discovery. So it was discovered through astrometry, but again, we have confirmed it using another method. So we don't usually use one method alone. We combine them. But this is what it looks like. Yeah, so we have our 2 stars orbiting around each other, and oh, wrong button. There is a star like the sun, yeah, that is orbiting a black hole of about 10 solar mass. And it does so in a period of 180 days, so about roughly 3 months. So it's a much different scale than the black hole we found with X-rays. And this is effectively just true of with astrometry. Instead, the shortest periods we can't detect, but we can detect much longer periods. So we have the shorter periods with X-ray, and then we have like something of a few months large, up to 10 years or so, that we can detect with astrometry. So they very nicely complement each other. Now let's look at spectroscopy. So again, my same universe, and I'm gonna highlight here one telescope, which is the Mercator telescope, which is a KU Leuven one. Now, before I'm gonna show you what spectroscopy would see, I want to tell you that spectroscopy is really costly. It's not like astrometry is not, but astrometry can do it, let's say, more efficiently because it can look at just all the stars at once. However, in spectroscopy, we need very, very high quality data to be able to say it's a black hole and not something else. So per system, let's estimate that we roughly would need 8 to 10 hours of telescope time. On top of that, if we look at just a random sample of stars in the sky and we would focus only on these massive stars, only 2% of them would have a black hole. So if we would observe 100 of these massive stars, which would already take roughly 900 hours or something, maybe we get like some candidates that we then again have to follow up because we were not exactly yet monitoring them as precise as we needed. We need more hours, and so it's very, very costly. We're getting better at this. We can take multiple spectra at once now, but to give you the idea, it takes a lot of time. But it is very fun because unlike, for example, Gaia or the X-ray telescopes, these ones are often on the ground. And so this one is the one that I got to use because I'm an observer. So this is the Mercator telescope. It's a 1.2 meter telescope, like mirror kind of, and it's located in La Palma in Spain. And so in La Palma, there are a lot more telescopes. And I want to just give you a rough estimate of the size of these spectrographs. So this is me, and this here, right here, is a 4-meter telescope, a mirror with 4 meters. But I don't know if you can see the scale, but the telescope itself goes super high. These instruments, they are massive instruments. And if you're lucky, maybe you get to see R2-D2 in some of the... but there is even more, right? This is only 4 meters. There are much larger ones. This is a 10-meter one. So this mirror here is 10 meter. to give you the scale of a human here, like the telescope is massive. So not only does it take a lot of time, I mean, you have to move. I mean, these things have to take a lot of energy to move as well. But a lot of fun, of course. Just wanted to highlight the massiveness of these spectrographs. So the other thing when you go observing is that, well, the night becomes your day, basically. So you wake up with the sunrise, sunsets, you have all these nice views. And actually, most of the telescopes that are in La Palma, at least they are next to a road which is publicly available. Not every observer might let you in, but with some telescopes, you can actually try and ask if you could go see them. So if you're ever there and you want to see like above the clouds, and you can see whether, check out whether some of them would allow you for a visit there. Highly recommended. But okay, let's go back to our data, to our universe. So I had a couple of stars here, but to highlight the spectroscopy, I'm going to add a couple more in my galaxy here. So I just added a lot more. So first off, these two, right? I mentioned the two black holes that we discovered in the other data. We have confirmed them. We know they are black holes, yeah? So they look like this one line that is moving from left to right. Now, spectroscopy is costly, as I said, so we're not really observing the whole sky. We're going to be selective. And as I kind of already spoiled you, most of them will just look like two stars moving around each other. However, once in a while, we do get lucky enough with the samples that we select, and we can find one, which was what we did a couple of years ago. Also big news, because it was actually published in Nature Astronomy. And this is what we call VFTS 243. That's just the number that we name it. So effectively, it moves like from just with one line. And this one is actually not even located in the Milky Way. It's in the Large Magellanic Cloud, so one of the galaxies close to us. And we found it's, again, about a 10 solar mass black hole and a 25 solar mass star in a roughly 10-day period. Yeah, so again, a different period range as astrometry and X-rays. And indeed, spectroscopy kind of falls in between the two. So we can go from very few days to up to a few years. Astrometry can go further. X-rays might be able to go much lower. So we're kind of nicely somewhere in the middle here. Now, what about free black holes? Because I've talked about black holes that are kind of orbiting around another star. So what about the ones that are alone, that are just roaming freely in the galaxy? For this, we also have a solution. We have microlensing. So what happens is, so we have this black hole, yeah? It's this very massive object in a very, very tiny space. So the gravity around it is so strong that it will actually bend light when light comes from behind it. So as a sketch here, or the GIF here, you can see that when the black hole is in front of a star, actually more light gets bent towards us. So we're going to see like a rise in brightness of the star. So all of a sudden, there's going to be a flicker in the sky. And then we're going to know that we have a black hole. So if we look at our galaxy here, let's try to find it, yeah? Okay. So, oh yeah, whoops. Okay. 3, 2, 1. Did everyone see it? Did we see it? Okay, okay, we can go again. No worries. Okay. I'll guide the eye a bit. I'll guide you there with the yellow one. We can do it one more time. There it is. And actually, we have managed to do this once so far. We have effectively discovered a black hole through microlensing with, again, a very, very beautiful name. This is just the instrument that discovered it. And it was discovered in the year 2001, and then just a whole bunch of letters to indicate what it was. So this is the different images that we took from it. So in 2011, you had this kind of very, very bright star. And as you can see, over the years, it kind of went very dim and it never got back up. So indeed, if we monitor it like over a lot of years, we can see, I mean, this is only the data of 2011, but you can see an enormous brightness peak, exactly also in the image. I mean, naturally, the image brights up. And so then it kind of just faints down, and it never got back up. But the fact, it's important that it never got back up, right? Because this tells us it was a one-time event. And this was effectively then after many years, so you can see it was only accepted as a black hole in 2023. So it took a lot of analyzing data and a lot of power to actually confirm that this was a black hole. It was largely debated, but now we do have one. So microlensing, we can also detect our free black holes. Now I've talked about the Milky Way, but what about like maybe very, very far galaxies? I said other galaxies, but I mean very distant galaxies. For this, we also have a technique, which is called gravitational waves. I don't know if you've heard about it, but a couple of years ago, it got like a Nobel Prize and everything. So what it basically is when two, for example, black holes are very close to each other, they will spiral around each other. And they have such a strong gravity that we will actually make ripples in space. And so what you can see here, right, in the image, they spiral in, and then you see at some point it will die out because there is no more rippling happening. And so we can actually detect this on Earth. So how would we do this? We have for this telescopes which have laser arms of 3 to 4 kilometers. So they are on Earth. They usually have 2 arms. They are called the LIGO, Virgo, and Kagura at the moment. One of them, Kagura, is located in Japan even. And so what happens if this gravitational wave passes through? Very simplistic, of course. There's much more happening. But it will kind of stretch out the space, and we kind of move our detector, kind of. And so this is how we would detect these black holes. And a lot of them have been discovered. Like hundreds of them have actually been discovered. So this is what we call the stellar graveyard, because, yeah, all dead stars, I guess. And so, yeah, gravitational waves has been very successful, but of course only in most of the distant galaxies. And actually, this is even a very old picture. There are many, many more now, even, and they are keep on being updated and updated. So I talked about a lot of the black holes that we have found. Now, this is our full picture of the methods I showed you. There is maybe 1 or 2 more methods that I'm not going to go into details about, but these are currently the main ones. So did we find enough according to our predictions? Yeah, are we happy with this? So according to predictions, there should be millions in the Milky Way. I don't know if you kind of recalled whatever I said, but there were only a few that I mentioned, right? Apart from gravitational waves here, that we have hundreds, but they are not in our galaxy, so actually we can't really count them in the predictions. We have these. Yeah, these red dots are kind of the black holes that we know of in our mostly in our galaxy. So I don't really see a million here. And effectively, this is true. We have very few that are found. Even with all these techniques, it's very difficult for us to find them. But there is hope. Yeah, Gaia, the telescope I mentioned, with its 2 billion stars, is going to have a new data release at the end of this year. So in December somewhere, astronomers are going to be very busy and celebrating their Christmas with data of this telescope. Because it's going to give us so much data, we're going to finally be able to really get into almost every star that it observed and try to see whether it has black holes. So this is going to be very, very, very big for us. The second thing is also there are more telescopes coming up. So there is the Roman Space Telescope, which is going to do microlensing. So it's just going to observe the sky constantly, monitor all the light sources. And it's going to do so for 10 billion stars. It's going to point at the center of the galaxy. It's going to observe so many stars. And it's going to be launched in 2027-ish, early, hopefully, if there are not too many delays. So this is
launching this year, actually.
So is it now confirmed?
Yeah.
Ah, okay, so it's confirmed. Oh, that's a first. Usually they only get delayed. This is great. Okay, I apologize. Okay, so it's even more exciting because it's going to be this year. And so, yeah, it's going to do a lot of, we hope to find a lot of events with this one. It's going to finally push forward our find for microlensing. Now, I want to also highlight the spectroscopic surveys. I don't have like an image of it, but because I said they cost a lot of time, they take time, we're getting better at this, right? We have telescopes that can observe a lot of stars at the same time. We have a lot of surveys going on from which we might detect candidates, and then so this is it's getting there as well. We might be able to like get a lot of improvements here as well to detect them. And then finally, on the gravitational wave side, there is a mission coming up which is called LISA, which is going to have instead of 3 to 4 kilometer laser arms, is going to have arms of like 2.5 million kilometers. It's going to orbit around with the Earth around the sun, kind of, and it's going to detect a lot of these gravitational waves, and it can even detect the gravitational waves or the black holes in our own galaxy. So Lisa will actually also be able to give us a little bit of a view of whether or not we have these very close black holes in our own Milky Way. So I think with these 4 major improvements that are coming up, I don't think the question is very few are found, but there is a lot of potential here that's going to happen in the next few years. So I think a lot of astronomers are very excited about all these upcoming missions. So this is kind of the sketch I have. I don't know if I still have like a little bit of time. Yeah, okay, well, that's great. The slide is going to come up again. So I now want to tell you what you should do or not do when you come across a black hole. So let's imagine you're on the road and you see this sign, black hole crossing. Okay, what's going to happen? What's going to happen? Okay, so at first you might ignore the warning signs. Yeah, there is a warning sign. It's going to be high gravity zone ahead. Stretching is going to happen. Because what's happening, you're at this black hole with such a strong gravity field that even a tiny centimeter closer is already going to be such a massive difference for you that your feet are going to be like pulled faster in than your head. So you're going to be going very, very long spaghetti string. That's basically what's going to happen. But that's not all. If you even ignore this warning sign, there will be a next one, which is time will slow down. When you get closer to the black hole, a lot of weird stuff is happening with your time because for you, nothing is going to change. But when we would see the person fall into the black hole, we're actually going to see them go slower and slower into the black hole. Until eventually, they might reach the point of no return ahead, and you can keep on ignoring the signs because it's a one-way only. There is really no U-turn available. Really, please do not enter this zone. And at some point, you're going to have entered it. And basically, what you can do is you're going to watch the end of the universe. Because time has slowed down so much right before you enter this zone that everything will just seem to pass by in a flash. And so what you will see as the person getting into the black hole is basically just the universe dying out. Whereas the other people that are just outside of the black hole, they will see you like freeze in the black hole. Yeah. So this is the kind of difference. So I would just advise you to not go in. Yeah. Just keep out. So I think that was my presentation.
So we have some time for question and answer. So please raise your hand and I'll call on you. And please wait for the microphone from Stephen. Yeah, back there. So, sorry.
Hello. I think you said that there were predictions saying that there are millions of black holes in the Milky Way.
Yeah.
What predictions said that? Or like, how did you know that?
Yeah, so these predictions are based on so we have the observational side, which is what I showed you, and then you have the theory side, which is these predictions. So what they do is they run a bunch of big simulations. So they say like this is a mock galaxy, like I created one, right? Like with my, I don't really have to go there, I guess. But so what they basically do is they take this, much more fancy, much more complicated, and they just let it evolve. So they let every star live its life and eventually die, and then they're gonna basically just count all the black holes. And so there is a lot of uncertainty in there, but given on the amount we know now, the ranges are like 1 million to 10 million or something.
Okay, can I ask one more question?
Mm-hmm.
Do you know like the ratios of the different types of black holes in the galaxy as well? Like you said, there's many types.
You mean?
Oh, I guess I'm confused because they're all similar but use different methods, right?
I just classify them according to method.
Yeah.
So all of these, and actually even also the gravitational wave ones, these ones are all just the stellar mass black holes that we call them. The only other different is these ones, right? These are the supermassive ones that we find in center of galaxies.
Okay.
Yeah, maybe a bit misleading. I just meant.
No, it's okay.
Yeah.
I was just confused. Thank you.
It's okay.
Patrick?
Kind of in a similar vein. I was thinking that of the methods, some of them are reliant on being binary systems,
Yes.
or with the X-rays, like having matter falling on them.
Yes.
Whereas, like my understanding is the microlensing doesn't rely on that. And so sort of to fill the gap between the theoretical prediction of how many there are and what the number actually observed, is there some sort of effort to, I don't know, make some kind of plot or distribution or something, particularly with the microlensing, to kind of extrapolate from there that, we've observed this many, but there could actually be this many or something along those lines?
So currently, as my understanding from the people who do the microlensing is that this single detection is fully compatible with there being 10 million in the Milky Way. Because the patch of the sky that we have observed is really not large enough yet. So the Roman Space Telescope is going to come up, is going to really change this, because especially in the center of the Milky Way, there are so many stars that we can observe. Because the chance alignment of a black hole going exactly in front of like a star is like, I mean, if you're not dense in stars, it's very tiny, and even in the center, it's already going to be quite so. So unfortunately, we cannot yet. Well, or it's still okay.
Right.
at the moment.
Okay.
But we might get there. Yeah.
Thank you.
You have a question?
Thank you, and this is very interesting. So I look into exoplanets, and I found that all of these methods are very similar to how we find exoplanets. And one thing missing is maybe a transit, which is the most popular method for exoplanet. And I wondered if a black hole does not emit light, similar to what happens for an exoplanet transit, if a star orbiting around a black hole goes behind the star, then that star will maybe disappear for a second or something, and maybe that's a black hole transit. Is that something that's considered?
So there is effectively, what I didn't talk about is another, indeed, like some form of like when you have the binary and, you know, the black hole is passing in front of the star, it will give similar changes, but more it will do some form of, well, I mean, it's not really microlensing, it's like, I mean, nano-lens, I mean, I don't know, like.
Yeah, okay, I know what you're talking about.
There's going to be maybe, depending on how close and how far it is, because like if it's too close or too far, it's also not going to happen. There is a fine range where maybe you'll have like a teeny tiny spike, but at the moment, our instruments are really not there yet to be able to detect like the amount of I think it's smaller than most of the exoplanets that we should detect, and something like this. I don't think that it necessarily will do a dip. Well, maybe if it's far enough.
So when it passes, so I get maybe if the star passes in front of the black hole as we're looking, then some kind of lensing event might happen. But what about when it's passing behind the black hole, which
it only happens when it's behind the black hole.
Oh, okay.
The star is behind. So we need, for the black holes, we need the star behind it, right?
Yeah.
So
and then
what can happen is an X-ray eclipse. So sometimes if you have this X-ray binary, when the star moves in front of the black hole, then all of a sudden the X-rays will disappear, and so we can see sometimes the dip in X-rays. But that works only with the X-ray binaries.
I see. Interesting. Thank you.
What about sub-solar mass scale black holes and primordial black holes?
Yeah, good question. Do they exist? No, the primordial for sure, right? But so the other ones, the teeny tiny ones, I don't think there is a way that I know of. Maybe you should ask the particle physicists. The primordial black holes is a whole different matter. I think because we're not really sure what they should look like, I think, either. So you mean the ones that are like not even coming from the first stars?
Yes, for example, and the one that some people suspected could be instead of Planet 9 or the dark matter,
right.
or
Actually, totally honest, I don't know. I guess if they would be out there and we would detect them with microlensing, I don't even know if we would be able to say, oh, a primordial black hole, because we can't see the black hole, right? So we can't really ask you where it's coming from. So I wouldn't know, I guess. Maybe if they have different masses, then we could try to see if they would have like, yeah, because a black hole, of course, I said they have 5 to 100 solar mass. Because if it comes from a star, it needs to have a certain kind of mass. So maybe if we find a black hole and we're 100% certain it's a black hole of like 1 solar mass, then I guess maybe we could say it's a primordial one. Because according to our physics and stuff, it shouldn't be able to exist from a star. But other than that, I don't know. Yeah.
Yes. And do we have a chance to actually have detected it in some microlensing data and just not being capable of recognizing it? Okay.
Who knows? Who knows? Sorry.
Oh, thank you for the talk. So for like the microlensing, you mentioned that it took like a decade for like a candidate black hole to be confirmed to be a black hole. But are there any like criterias or like, I don't know, like a checklist for astronomers to confirm that like a candidate object actually a black hole? So
I think, so just from microlensing alone, it's quite difficult because you have a lot of degeneracy, right? So if you don't know how far your black hole came in front of the star, you need to know how far the star was. You need to know what kind of star we're looking at. Like there are a lot of things that we don't know about it. So we always need some kind of follow-up of this. But I think when we want to check whether it's a black hole, a very important thing is that we also look at it with astrometry. Because not only does all of a sudden the blink of light change, but I don't have a cartoon of it, but when the black hole passes in front of the star, it will also appear to shift the position of the star. So in astrometry, it might kind of, yeah, I don't know, the star might do something like, I mean, it's not really like this, but it will appear to have this kind of weird motion that's not supposed to be there. And so this astrometric microlensing actually takes a lot longer before it's done. So this is, I think, why it took so long, because they needed to confirm also with the astrometry that effectively, you know, it's a black hole and not just a neutron star, or not 2 stars, or not. It can get very complicated in microlensing. Yeah, did that kind of?
Oh, it's okay. Thank you. Also, out of curiosity, I wanted to ask that you mentioned for like a spectroscopy, like if there's like 2 stars and one is missing, that it's a black hole. But is there a chance that there might be like 3 stars and one of them is a black hole? So it looks like there's 2 spectroscopy moving, but there's actually one missing.
Yeah. Yeah, and also, I mean, I made it quite simple for the presentation, but it's not because we only detect one line that it's a black hole, right? This is why spectroscopy is so difficult. But technically, I think you can make any method as complicated as you want, and you probably, as long as the universe can give it to you, you can do it. So you could have a system where you have a star and a black hole orbiting around each other, and you could have a 3rd star around it, which you would see, but you could also have 2 stars with the black hole around it, and then it would be much more difficult to detect, because this black hole will have a much longer period. And so you would have to monitor it very long time to see that actually this inner binary is actually going like this as well, instead of just, but definitely possible.
Thank you.
I think that's all the time we have for questions, but if you didn't get to ask your question, please stay afterwards and talk to Soetkin about it. So let's thank her again.